Alright. I don't want to be recorded. So I'm gonna. You just spoke and you just got recorded. Alright, we're gonna look at electrical safety. Alright. Now, household electricity, we normally use about 230 volts RMS, and it's at a frequency of 50 Hertz. Now, don't stress too much about this bit. I'm going to mention it. You don't need to know about it until next year, but I'm going to mention it anyway. RMS means root mean square. If you don't know what that means, that basically means you take the average, and the highest average of it is 230. So, the actual voltage that you get, if you have a look at the graph, it can go up to 325. You do need to write down the fact that your household voltage is 230 as an average, so somewhere between 220 and 240. But the other one that you need to write down is this frequency part. So F equals 1 over T. Now you're told that the frequency is 50 Hertz. So if you use the formula there, F equals 1 over T. I'll fix it. Sorry. Trying to fix it. If you use F equals 1 over T, then you get 1 over 50, which then tells you, oh sorry, not 1 over 50. Hang on.
Very inspiring slide.
I can totally see it.
So, can't see what I just wrote on screen, but F equals 1 over T. Our frequency was 50 Hertz, which is 1 over T. So if you rearrange it, it's 1 over 50, which then tells you it's 0.2 seconds for every fluctuation. Alright. Now, if you went to the excursion, you'll remember all three of these, hopefully. There are three things that in your household that are used to stop electric shocks and also appliances from dying. You have a fuse or circuit breaker, you have an earth, and then this is a connection which shows you both together. Now, most of you will know what a fuse is by now. What's a fuse? Come on, a fuse. Correct. So, it's a short piece of wire that melts. Okay? It's a short wire that melts when there's too much current going through. Circuit breaker. If a circuit breaker, in the most basic sense, uses magnetism to break the connection. So basically, as the person described it, there is a set of magnets inside, and as the magnet trips, there's too much on the magnetic field, so then it will separate, which means the connection is no longer joined together. That's why a circuit breaker is much better for that. Alright, last one is earth. What is earth? Yes. Correct. So it directs the current towards the earth. Alright, anyone have any questions on that? Alright, so there are a few other things we need to look at. One of them is power ratings. So power rating is this thing here in watts. What does that mean? It's power. So remembering that power is either the voltage times the current. It's either the voltage times the current or current squared times the resistance or voltage squared over the resistance. You will be using one of those at least to figure out some of these questions. So please make sure you write that down somewhere in your formula sheet. Depending on the formula sheet, you may only get P equals VI, and that's about it. So please make sure that you have them down in your formula sheet, on your summary sheet, regardless of whether or not the formula sheet has it. Thank you. All right. A toaster is rated at 1,400 watts at 230 volts. A, what current does a toaster draw when operating normally? So we need current. We have the power. And we have the voltage being 230 volts. So how do we find the current? Which version of the formula should we use? Very good. So P equals VI. So our power is 1,400 watts. Our voltage is 230 times the current. Very good. So then 1400 divided by 230 gives us 6.09 amps. Alright, what is the resistance of a toaster element when hot? So again, we're told power, we're told the voltage, but we need the resistance this time. So which one should we use? You good? You're assuming you've worked out the current correctly, though. Should we presume that we worked out the current correctly? I don't think we should. What if I made a mistake? You can't trust me with that. So maybe use V squared over R. Then rearrange it. And it should give you 37.79 ohms. Now, when you are paying for electricity, please be very careful. The units that you use is kilowatt hours. However, what you need to think about is this. Kilowatt hours is actually the same as the power, because power is in watts and hours is time. Because you have power times time, it is the same as energy. Now, you need to be careful because of a couple of things. Number one, what is the voltage set at in your house again? 230. And we know that this is based off power and time, so really, as long as you know the power of every bit of equipment in your house, what does it essentially calculate? So I'll give you a hint. You know most of the things in your house are told with power. So what does your house usually count? It's just the time. So you're actually being charged for how much time you use your equipment. Okay? Now, I'm going to write down something very important. You may or may not be asked to convert between kilowatt hours and joules. Please make sure you write this down. You will most likely be asked on how to convert it. I'm going to show you how it works. You can at the end obviously just write down the very last line, but you may be asked to convert it, so make sure you know how to do it. How many joules does 1 kilowatt hour represent? So, 1 kilowatt hour. Now this is a times, so sometimes we can denote the times with a dot just to make it look a little bit nicer. What are the SI units for power? Watts, very good. So this kilo, we need to convert it into kilowatts, we need to convert it back to watts. So what's that? 10 to the power of 3, very good. Now, what time do we normally use in SI units? Seconds. So we need to convert 1 hour into seconds. So how do we convert it to seconds? What'd you say? 3,500. Not quite. All right, if you're not too sure, just to make sure. 1 hour has 60 minutes, and then each minute has 60 seconds. So that's 3600,000. Hang on. Watts times seconds, so that's in joules. Or if you like, 3.6 times 10 to the power of 6. Please make sure you write that down. 1 kilowatt hour is equivalent to 3.6 times 10 to the power 6 joules. Then, from now on, you can just simply use that conversion to figure out what you need. So if you need 2 kilowatt hours, what do you need to do? Just times that by 2, right? So that gives you 7.2 times 10 to the power 6 joules. Nice and easy, right? Now, you might then think that number seems really gigantic, and it is, but that's the reason why, but then you might also want to think about how much you pay for electricity. You might not actually pay that much. You might be surprised. Does anyone know how much you normally charge for electricity? It's like 0.23 cents per kilowatt hours or something like that. So that's the reason why if you look at your household electricity bill, mine, for example, every month, every month I only pay like $50 or something like that, or 30. It's not that expensive. Technically, no, that's how much I get. That's how much I pay without solar panels. So technically, if you chose to install solar panels, you could even be getting it for free or getting it paid back. Did you guys know that? If you install solar panels,
So we have 7 solar panels.
yeah, but eventually you don't even need to pay for it because the government kind of pays you back. Because it takes your electricity and feeds it back into the system. Yeah.
So when you install solar panels, they found that their electricity bill got higher.
That shouldn't happen. Alright, I'm going to continue. Remembering that there's a lot of slides here, so I'm going to keep going. Alright. A television draws 0.37 amps of current when connected to a 230 volt supply. A, what is the power rating? How do we figure that out? What is this? Current. What is this? Voltage. So we want power. Very good. So 0.37 times 230 is something. Bless you. Yep. Now normally on equipment it would just say 85, just so that you know, because it doesn't like decimals. How much energy does a TV consume if it is operated for 5 hours a day for 4 weeks?
4 weeks.
Now we already have the power. Hang on. We already have the power. So all we need to do is power times time. Now remembering that we need to convert everything into, oh sorry, we don't need to do that. Alright, I'm going to do a little cheat here. I'm going to convert this to kilowatts. Why? See on the bottom how it tells you, and remembering that I told you, you're charged by kilowatt hours. If we convert it to kilowatts now, we just simply need to multiply the amount of hours and we have it in energy. Obviously, this doesn't tell us what unit you need to answer in, so you can pick whichever unit you want to answer in. Alright, how much energy does oh there you go, that's how much you get charged, 16.381 cents. How much energy does the TV consume? So it's 5 hours. For a day for 4 weeks. How many days is that? 7 days a week for 4 weeks. So 0.085 times 5 times 7 times 4. And like I was saying, we're not paying anywhere near what we should be paying for electricity because 11.9 times, well, it's 16 cents, so I'm just going to convert it to dollars now. One key thing, please make sure you include all the other decimals for, sorry, what was it? Okay. Yep. Like I said, we're not being charged anywhere near enough. That's why the carbon tax is technically meant to happen, but different story. I'm not going to go through that. You can ask Josh about that. Josh, are you listening, Josh? He'll watch it later. Alright, let's keep going. Everyone got the sound? Yes, yes, yes. Can I continue?
Yes.
Is this relatively clear to everyone on what I did?
Yes.
Hopefully. Alright, stuff you need to write down. Electric shocks. As I told you, the exact frequency and RMS value of AC is really dangerous for human beings, which is why when we went to the excursion, make sure you write these all. Which is why when we went to the excursion, they mentioned that people did consider switching to DC because DC obviously avoids these issues. Some of you have touched DC before, so Caitlin, you were holding on to DC current. If you remember, on the dome, that's technically DC because it's direct. It's only going through your body and back out. So that's DC because it's only going in one direction. Alright. Now, due to different reasons, that could affect the different ways you could get shocked. So I will be asking you something about this. So you need to know enough about it. There's a table for each part. They'll tell you, table for some more parts. Later on, they'll tell you exactly what you need to do. You just need to give some brief descriptions as to how each thing affects you. Now, resistance of the body is the first one. That's dependent more about whether or not your hands are wet or dry. On a dry day, obviously, it's affected differently compared to, say, when your hands are wet. Effective current. So, how strong your current is. Obviously, the stronger the current, the worse it is for you. And that's kind of dependent on the first one. Current path. When I'm saying current path, that's the path it takes through your body. So which part would you suspect that if it hit you straight off, you'd be pretty much dead? Heart, what's another one? Brain, or spine, could be any of that. Anyway, there's a table showing you what happens to that later. And then time of exposure. So if you get exposed to the current for a longer period of time, obviously that's worse for you. Pretty straightforward, right? I say that, and then people don't write it down, and they don't give the correct answers for the SAC, so can you please make sure you write it down?
Electricity.
Alright, is anyone still writing?
Nope. He says still writing.
You better memorize it.
Alright, let's keep going. Alright, resistance of a human body. So if you're wondering, human skin range can go from 1,500 ohms to 10 to the power 6 ohms. That means if your hands are wet, the voltage, the current will be higher. Now, if you have wet hands and you have versus dry hands, which one gives you the higher current? Wet hands. And what can you use to find that? I'm not going to go through it here, but what can you use to find that? Ohm's law, very good. Please make sure you know and remember Ohm's law. Alright. So resistance to dry skin is up to 600 volts. So technically, if you did touch the plugs in the wall, you're meant to be safe. But, you know, it's not really that safe. Alright, and you've seen this before. We're made up of mostly salt and water, so we conduct electricity really well and we'll blow up, etc., etc.
That's really nice.
I'm just going to keep going. You can write this down later if you need to. Effective current. So, current causes muscles to contract. I'll show you the video a little bit later. At the same time, stimulates the brain. Then you can read this one a bit about what current does. You don't have to memorize the whole thing. You just need to know. You just need to know what current does to you. And then, if you look at the bottom here, a current as low as 25 milliamps through the trunk of the body can cause fibrillation. Fibrillation means it will cause your heart to have disorganized beating. So that's why, if you want to restart someone's heart, what would you use? Defibrillator. Okay? Current path, the different paths in your body obviously affects you. And the last one is the time of exposure. I would suggest you copy this table somewhere in your summary sheet. I'm not gonna this is the really basic version where the amount of time tells you how much it affects you. So if you're connected for more 4 seconds or more, you're pretty much going to die. So part of the problem though is once your hand is in a plug, what happens? Your muscles contract, which means it's really hard to pull it out. So that's why if you touch electricity, it's usually not great for you anyway. That's why there's other things to stop you, such as what's one of the safety features? Circuit breaker, or fuse, or any of that stuff. Okay. And so this one will be the effect one. How does half a second of electricity affect your body? There you go. There's all that stuff. If you have 500 milliamps, look at how dangerous it is. Yep. Hopefully you know about this part. If in the event of an electric shock, what should you do? What should you as a bystander do?
Get a wind stick and whack him.
Yeah. Get something that doesn't conduct electricity to remove them from the spot. Please do not use the chairs you're sitting on because obviously there's metal underneath.
Or join in.
No. You guys get the idea. Alright.